Hello, and welcome to Differential Equations. This is Lecture 7, Autonomous Equations. Last time, we talked about exact equations. So this is an equation that in differential form notation, we would write as mdx plus ndy. And what we saw is that you can write this as the total derivative of some function psi, if and only if the derivative of m with respect to y, right, which would be equal to the second derivative of psi with respect to x and then with respect to y, would have to be equal to the derivative of n with respect to x, because that would also be equal to the second derivative of psi, right? So that's clearly a necessary condition, and we saw, or rather I told you, that on nice domains, it's also a sufficient condition. This time, we're going to discuss some of the qualitative behavior of some first-order equations. Okay, so the type of equations we're going to be looking at are autonomous first-order differential equations. An autonomous differential equation is one where the independent variable so for which we usually use the letter t, does not show up explicitly. Right? So that is to say, it's an equation that looks like dy by dt is equal to f of y. Okay? So notice that if f of y naught is equal to 0, or some constant value y equal to y naught, then this constant function solves the differential equation. Right? Clearly, since the left-hand side would be 0 because the function is constant, and the right-hand side is 0 by assumption. These values are called equilibrium solutions or equilibrium points. Okay. So many things simplify because the independent variable doesn't show up explicitly. For example, let's think about the slope field. Since the equation does not depend on t explicitly, there is no need to draw the whole plane. Since any vertical strip will just be repeated. Over and over. So it is enough therefore to draw what's called a phase line. Right? We just keep, say, the y-axis and we draw an arrow pointing up when f is positive, an arrow pointing down when f is negative, and a dot at equilibrium points, right, which are points where f equals 0. Okay, so let's do an example. So to find the phase line, also called slope line, of the equation dy by dt equals y squared minus y minus 6, let's note that here f of y, y squared minus y minus 6, you can factor as y minus 3 times y plus 2. And so this is going to change sign at the points where it vanishes, at y equal to 2 and y equal to 3. Right? So if all we want to know is what sign does f have, we only need to keep track of what happens on either side of each of these points. So we start with, if y is less than minus 2, then what happens? Well, so if y is less than minus 2, then this is going to be negative, and this is going to be negative, and negative times negative is positive. So f of y is positive. If we're in between minus 2 and 3, then this is still going to be negative. This is now going to be positive. And so negative times positive is negative. And then if y is greater than 3, then both of these factors are positive, so we end up with positive. Right, putting these together, we can draw the slope line. So the slope line is going to be the y-axis, right? And we're going to put a point at minus 2 and a point at 3. Right? And then let's see, below minus 2, we got f positive, so we have arrows going up. In between, f is negative, so we have arrows going down. And then greater than 3, f is positive, so we have arrows going up. Right? So this is the slope line. Right? And the phase diagram, the slope diagram would just be the plane with this repeated over and over. Okay, so what do we learn from this? What do we learn from the slope line? Well, let's think about what happens to points that are not at equilibrium, but they're close to equilibrium. So notice that y values that start out close to, but not equal to 3 will move away from it, right? Because if you're not at 3, but you're nearby, well, if you're a little above, then you're going to start moving up. And if you're a little below, you're going to start moving down. While y values that start close to -2 will move towards it. Okay, so we give these types of equilibrium points names. So an equilibrium is said to be stable if nearby points move towards the equilibrium, and unstable if nearby points move away from it. Stability is very important from the point of view of applications. Stable equilibria are, in some sense, self-correcting. Right? If you start near it, then the dynamics will evolve to move the solution closer to it. Right? If the equilibrium is unstable, then the dynamics tend to move the solution away from it. You don't expect to observe unstable equilibria in real life. since any small change in conditions, things like experimental error, move the system away. Right. So you can think of this as like what happens if you were to drop an iPad, say, right? While it's entirely possible that you could carefully balance an iPad on its edge, right? That's an unstable equilibrium. Almost surely you're not perfectly balanced on the edge and you're going to land flat on one side or the other. Okay, let's consider a very simple example, in some sense the easiest autonomous equation that's not trivial. Consider the linear autonomous equation, right? dy by dt is equal to some constant times y, right? Linear homogeneous autonomous equation, right? So if k is not equal to 0, then there is one equilibrium point at, let's call it y star equal to 0, right? Its phase diagram, well, its phase diagram depends on the sign of k, constant k. So if k is positive, then we have this point 0, right? And k times y is going to be positive for y positive and negative for y negative. So that means we're going to be moving up or down. And if k is negative, then we similarly have the origin. 0 is the only point, but now if k is negative, this is going to be negative for y positive, positive for y negative, which means we're going to have arrows going down when we are y positive and moving up for y negative, right? So its equilibrium is unstable for k positive and stable for k negative. Okay, so as we've mentioned before, one of the reasons why we really like to study linear things, besides the fact that they're simpler than nonlinear, is that then when you have a nonlinear thing, like a nonlinear differential equation, you often study it by approximating it with linear. So that's the case as far as equilibria go. There's a theorem known as the Hartman-Grobman theorem. Right? It's named after Philip Hartman, an American mathematician, and David Grobman, a Soviet mathematician, who both proved this roughly in 1960. And so this theorem says, suppose y star is an equilibrium point for the autonomous equation dy by dt is equal to f of y, right? So it's an equilibrium point, so f of y star is equal to 0. Then if the derivative of f with respect to y at the point y star is positive, equilibrium is unstable, right? So just like we had here, right? And what's more, you really can approximate it with the linear equation pretty well, in that solutions that start near y star are not equal to it. Move away exponentially, right? So just like in this linear equation, where we know the solutions are exponential functions, right? Similarly, if df dy at y star is negative, the equilibrium is stable, and solutions that start near y star move towards it exponentially. The third possibility, right, if df dy at y star is 0, then the theorem tells us nothing. So we'll just write then further analysis is necessary. Okay, so we're not going to prove this theorem, but let's wave our hands a little about how it's proven, right? So the idea for the proof is to write y as y star plus something small. So some function v, let's say y of t, is y naught plus epsilon times v of t, right? Here, epsilon is something we think of as small when y is close to y star, right? So if that's what y is equal to, then the derivative of y with respect to t would be equal to epsilon times the derivative of v with respect to t. But on the other hand, this is equal to f of y, and we've decided that y is y naught plus epsilon v, right? Writing f, not y naught, sorry, y star, f of y star plus epsilon v as well, it's Taylor expansion, right? So it's f of y star plus epsilon times the derivative of f with respect to y at y star times v plus big O of epsilon squared, right? So big O, in case you haven't seen this notation, this just means this is a term that for epsilon small is bounded above by epsilon squared. So it's something that's going to 0 as quickly as epsilon squared when epsilon is going to 0. We know that f of y star is equal to 0, right? Because y star is an equilibrium point. So this says that the right-hand side of this equation looks like epsilon times this derivative plus something that's small, like epsilon squared. So this leads to epsilon dv dt is roughly epsilon df dy at y star times v, right? So this leads to the equation dv by dt is equal to, let's say, k times v with k, this is a constant, this df dy at y star. And so we have sort of reduced to the linear case. Right? And since we've already analyzed the behavior of the linear case, we would conclude with the conclusion of the theorem. Okay, let's do another example. Let's look at the logistic equation. Right, so remember, this is used to model population growth when you have a finite carrying capacity. Right, so we have two constants, two parameters, k naught, just like a rate of growth, and then p naught, which is the carrying capacity. Right, but you notice that t does not enter explicitly, so this is an autonomous equation. Let's suppose, as usual, that k naught and p naught are positive. Right? In this case, we have two equilibrium points. P equal to p naught and p equal to 0. Right? So here, the right-hand side, f of p, is equal to k naught p, p naught minus p. So the derivative of f with respect to p, right? Notice that you take the derivative of f not with respect to t, not with respect to the independent variable, but with respect to p in this case, or y in our usual notation. You take the derivative with respect to the dependent variable. In this case, this would be k naught times p minus 2 k naught times p, sorry, k naught times p naught. And so this factors as k naught times p naught minus 2p. Okay, so let's look at these two equilibria. At p equal to 0, we have this derivative evaluated at p equal to 0 is equal to k naught p naught, which is positive. So this is an unstable equilibrium, while at p equal to p naught, we have this derivative is equal to minus k naught times p naught, right, which is negative. So this would be a stable equilibrium. And if you think back to when we worked out the phase diagram for the logistic equation, right, the if your population is at 0, then anything, well, 0 of course is stable, but if you have any small amount of population, this model would have that population grow approaching p naught, right? So p equal to 0 is unstable, whereas if you are at full carrying capacity, then that's an equilibrium. But if you're near the full carrying capacity, then this model moves the population towards it. So a stable equilibrium. Okay, let's do one more example. This is a bistable. The system is called bistable if it has two stable equilibria. So think, for example, of a light switch, right? The light switch is stable at the on and the off position, but it might have like an unstable equilibrium halfway in between. Like maybe if you balanced it really carefully, you could get it to stay halfway in between, but that's unstable because you move it a little bit and it'll either pop all the way up or all the way down, right? In electrical engineering, circuits with bistable behavior are commonly called flip-flops. And are important design elements as they form the basis of logic gates. Okay, so concretely, consider this equation. dy by dt is equal to y times 1 minus 2y times y minus 1. Right? So note that f of y is equal to 0 if and only if y is equal to 0, or y is equal to 1/2, or y is equal to 1. Right? So those are our equilibria. And we want to think about whether they are stable or unstable. Right? Let's go ahead and work out the phase line. So these are the 3 points where the sign is going to change. So we need to consider what happens in the intervals cut out of the real line by these points. If y is negative, then, well, in this product, we would have negative, positive, negative, right, which would give us positive. So f of y would be positive. If y is in between 0 and 1/2, then we'd have positive, positive, negative, right, which would be negative. If we're in between 1/2 and 1, then positive, negative, negative, right, which is positive. Y is positive. And then finally, if y is greater than 1, then positive, negative, positive, negative. So f of y is negative. Right? Hence, the slope line is as follows. We have 0, 1/2, and 1, right? Those are equilibria. And if y is negative, then f is positive, so we're going up. If y is in between 0 and 1/2, f is negative, so it's going down. If y is in between 1/2 and 1, then f is positive, so we're going up. And if y is greater than 1, then f is negative, so we're going down. Right? So we see that this is a stable equilibrium, this is unstable, and this one is stable. Okay. Excellent. So the class ends there. Feel free to stop watching the video. For the next historical context, I want to tell you about some of the names that have come up, namely Johann and Jakob Bernoulli. So some of the first people to learn calculus and advance it after its initial development by Newton and Leibniz were the two brothers, Jakob and Johann Bernoulli. The father of these two brothers was a prominent citizen of the Swiss town Basel by the name of Nicolas Bernoulli. He was a spice merchant in Basel, and he wanted his children to study something practical, but these two went against his wishes and ended up as mathematicians instead, although they did very well as mathematicians. It's a really remarkable family in that in these 3 generations, they had a bunch of prominent mathematicians. And if you keep going, they have a bunch of prominent scientists in many different fields. But here, let's just write down their family tree, and I'll put numbers, Roman numerals, next to the ones who are mathematicians. Because although the family was very creative as far as their mathematics and their scientific endeavors, they were not creative as far as naming. So let's start with Nicholas. And so he had 3 sons for this purpose. Jacob, who we'll write as Jacob the first, because he was a mathematician. Another Nicholas, who had a son, Nicholas, which I'll denote Nicholas the first because he was a mathematician. And then we have Johann. Well, note Johann the first because he was a mathematician. Then Johann's children included mathematicians, so we'll put Nicholas II. Daniel the first. Johann the second. And then Johann the second had children. Johann the third. Daniel the second. Nicholas III. And Jacob II. Right. So again, I'm only labeling with numbers the ones who were mathematicians, not like this Nicholas is not the first Nicholas in the family. He's just the first Nicholas mathematician in the family. So you can see that they had many mathematicians in these 3 generations. Right. So it was a very impressive family. Okay, but right now I want to just talk about Jakob and Johann. So Jakob, who was alive from 1655 to 1705. So that makes him basically 10 years younger than Leibniz, right? So pretty much a contemporary. So he studied philosophy and theology at his parents' insistence, right? This was meant to be practical. They wanted him to go into the church. But while he was studying this, he studied mathematics and astronomy on the side. And he was appointed professor of mathematics in Basel in 1687 after some scientific travels before that. Johann first, so his dates are 1667 to 1748. So you can see he was basically 12 years younger than his brother, Jakob. So his parents wanted him to study business. And in fact, they made him work at the business when he was 15 or so. But he ended up being pretty bad at that. So he got permission from his parents to go to college, but they insisted that he study medicine. So he got his degree in medicine. But while he was there, his brother was already professor of mathematics. And so Johann would, in his free time, study math with his brother Jakob. They worked together to understand Leibniz's papers on calculus, and they made a lot of progress in calculus in the early days. But after a while, they had a big falling out. They accused each other of stealing results, and Johann eventually moved away to Holland. In 1695, they stopped talking to each other basically in 1697. When Jakob died, Johann moved back to Basel and took Jakob's job. So there was only one professor of mathematics at the University of Basel. For a while it was Jakob, and when he died, it was Johann. Jakob is, among his many contributions, Jakob is the one who started calling the integral, what we call the integral, he called it integral. Leibniz introduced the notation, but he called it something else, something like summa infinitum or something like that. Jakob showed that the sum of 1 over n is infinite, for example. He showed that the sum of 1 over n squared is finite, but he wasn't able to figure out what it sums to. That took a little later. Euler was the one who figured out what that converged to. Jakob, we talked at our last historical contact, we talked about the Bernoulli cone, the cycloid, and I mentioned that Christian Huygens had shown that it was also the tautochrone. Jakob showed using differential equations that the cycloid was the tautochrone, right? He solved a separable ODE to do that, much like the Bernoulli cone that we talked about. We talked last class about the Bernoulli differential equation. That's named after Jakob. He's the one who came up with that trick, the substitution that reduces it to a linear differential equation. But probably Jakob's greatest contributions were in probability. He wrote a book called Ars Conjectandi, which means something like the art of conjecture. It was published after he died. And in this book, he discusses the theory of interest, right? So the number E, right, Euler's number, we call it, that was actually first defined by Jacob Bernoulli, although it became really famous through Euler's work. He also came up with Bernoulli random variables. If you've taken any probability, then the simplest random variable is the Bernoulli. That's from Jakob and his book Ars Conjectandi. Also there, the Bernoulli numbers came up. So if you probably haven't run into these yet, but if you study lots of complex analysis, you definitely will. It's also where the law of large numbers shows up. So this is the idea that if you perform an experiment sufficiently many times, then the observed ratio of success will converge to the expected mean, the expected value. Johann is the one who came up with the brachistochrone problem that we talked about at our previous historical context. And I was telling you about Bernoulli's solution to it. It's this Bernoulli, Johann. The way math was communicated back then often involved posing challenging problems to other mathematicians. And that's what Johann did with the brachistochrone problem. So he posed it as a challenge to mathematicians. Who can find what curve will allow a bead to go without friction using only gravity from point A to point B in the shortest amount of time? He received 5 correct solutions, including from his brother Jakob, including from Leibniz, and also including from Newton. The story is that Newton was told of the problem one day in the afternoon while he was working at the Mint after he had basically stopped doing research. And that day after dinner, he stayed up late and solved the problem. It took Johann 2 weeks to solve the problem. But Newton was able to do it in a night. He submitted his solution anonymously, but when Bernoulli received it, he is supposed to have said, I recognize the lion by his paw. And clearly the solution could be none other than Newton's. In 1691, when Johann was traveling through Paris, he met a very good French mathematician, Guillaume de l'Hôpital. He was very good, but he was not as good as Johann Bernoulli. And Bernoulli agreed to teach l'Hôpital calculus. L'Hôpital paid Johann a great deal of money for these lectures, and even after Bernoulli had left Paris, because he was only traveling, he continued to send lectures by letter to l'Hôpital explaining calculus. L'Hôpital, in 1696, published the first ever calculus textbook based on Johann's lectures, but not acknowledging that it was based on Johann's lectures. He just says something in the acknowledgments that he's very grateful to the brothers Bernoulli, to the gentlemen Bernoulli, for all of their discoveries in calculus. So, for example, the famous theorem, L'Hôpital's theorem that you learn in calculus, that actually should be Bernoulli's theorem. It should be Johann Bernoulli's theorem. It wasn't until 1922 that it was established that Johann had written, or that L'Hôpital was just publishing Johann's lectures. Johann started claiming this in 1704, but nobody believed him at the time. The reason people didn't believe Johann is Johann had a history of getting into rivalry disputes with people and not always acting very ethically. He had bitter rivalry with his brother Jakob, as I already mentioned, leading them to stop talking to each other. And in fact, for the brachistochrone problem, one of the solutions Johann received was from Jakob, and Johann tried to pretend like that was his solution. Also, after Jakob died, Johann ended up in bitter disputes with his son, Daniel, specifically about hydrodynamics. They both wrote about hydrodynamics, and Johann tried to pretend that he had written his book before Daniel had written his, even though, in point of fact, Daniel wrote his first. Also, when Johann was a professor in the Netherlands before he inherited Jacob's position in Basel, he got into a dispute with one of his students, and he even published letters talking about how stupid his student was. So Johann was not an easy person to get along with. And it wasn't until 1922 that letters were discovered showing Johann Bernoulli explaining to L'Hopital how calculus worked in much the same way as L'Hopital's textbook. And so it's only after 1922 that it's established that Johann should get the credit for L'Hopital's discoveries. Nevertheless, despite being very hard to get along with, Johann was very famous during his life and was known as the Archimedes of his age. And in fact, that's what's inscribed on his tombstone. All right, we'll stop there and pick it up from there next time.